Okay, so this document I have up on the screen is your second HAP, Hourly Analysis Program homework. So it's along the same line, so you can use that same initial file that I sent to you. So the base case, and we're just going to run some different chillers and look at the impact on the energy use and all that sort of thing for 4 different chillers and compare those to that water-cooled centrifugal. Please notice I asked you to change the chill water temperature to 42. I think we ran 44 in that first homework. And so you have to be a little careful. You have to get in there and make sure in the chiller definition and all that sort of thing. And there's a chiller definition and there's a chiller plant definition. And you need to check both of those and make sure that they're set on 42. I don't know if those chillers were defined. If they are, you may already have the absorption in that file. My intent would have been to delete them before I send them to you and let you build them, but you know, the best laid plans sometimes go astray. But you need to look through all of those and realize that for these absorption chillers, you'll need a different size cooling tower. So you'll have a different flow rate. It's okay with me if you use the default flow rate for those. I think the single stage comes up with 4.5. I think it's 4.5 GPM, but I could be wrong. But if you define one of those chillers, then part of that definition in the chill water plant is to define a cooling tower. And so it knows that it's doing a cooling tower for an absorption. And so it should give you a higher flow rate than 3 GPM per ton. If you're at 3 GPM per ton, then you need to increase it. 4.5 GPM is fine for those. So all 3 of the absorption will need to have cooling towers defined for them if they're not already in there. And then of course the air-cooled screw, air-cooled implies that you don't need a cooling tower for that one. So it dumps its heat directly to the air. Okay, so also, and this may already be in that model, but if you don't have a heat source for the absorption, then you'll be told that you have to add one. And so if that's not in there, you'll be prompted to define a steam boiler to provide heat for the first 2 absorption chillers. Now the direct fired, you know, it burns gas itself, so it's its own source of heat. And so what I've done in there, and I think it's already in the file, but so the hot water boiler is defined to provide the space heating energy, and that's what you've been using on the first assignment. And so then, and the reason I set it up that way was so that you could see the difference, because you can, in the reports, you can see the energy for the steam boiler. Well, that'll be the energy to drive the absorption. And then you have the energy of the hot water boiler, and that was to provide the space heat. So defining those 2 different types of boilers lets you see what that what those absorption chillers are actually requiring in terms of a natural gas input to create the steam that it takes to drive the chiller. Okay, so let's see, then for pump heads, and this is in the chiller plant definition, you'll probably need to change. I don't know what they're set on now. What I sent, they may be set on this, I'm not sure, but you'll need to check. So, so the amount of pressure produced pump head is pressure. And so for the chill water pumps, just go ahead and use 50. And for the condenser water pumps, I said use 70. And now, you know, in a real design, you would have to calculate the pressure drops all around the system. And then you would put in the actual number. But, you know, these are halfway reasonable numbers. Whoops, going the wrong direction here. Okay, what did I say on the steam boiler? Well, I've already said some of that. In that boiler definition, there should be boiler accessories, and I'm thinking that's like combustion fan that would be associated with a boiler. Said, 5 kW, that's about 7.5 horsepower, which, that's reasonable size for a boiler. So make sure that that's defined at 5 kW. Let's see, from the output data, just take that Excel sheet that you already have, and you can kind of copy those categories. And I don't know if there may be, you may want to break out the steam boiler energy for absorption and then the heating boiler energy. So you may want to add, a heading or two, but basically something like that spreadsheet where you look at all of the different energies and just kind of see, what happens to the different energy totals and then the cost of operating the building as we go from these different types of chillers. I think we'll probably see the absorption cost will go up because we haven't really tailored this in a high demand situation like was in that example, those example slides we went through from Train. And then I asked a question down there. In this is thinking about if the heat input came from a waste heat source like it could in some sort of an industrial plant, if the cost of fuel for the steam boiler was zero because it was recovered waste heat, how would this change the outcome of the study? And so see what the absorption would look like compared to the others if you didn't have to spend money for that steam boiler gas. And of course, another question is maybe you could do space heating. Maybe you had enough waste heat that you wouldn't have to run the hot water boiler, but I didn't ask you to do that. And then, put all that together in your Excel sheet. And, you could type just a little discussion, and it doesn't have to be a lot. Just say, well, blah, 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 absorption looks good if the heat's free, or, just whatever you think when you look at the numbers. And so that's roughly due a week from today. If it's a day or two early or late, that's fine. As you can tell, I'm not just real good at grading homework promptly, even though I have been working on them some, but I don't have them all back to you yet from the first assignment. Okay, any questions or comments on that? I sent you an email a little while ago. You may not have had time to look at it yet, but there's a number of files along with this in there. Okay, so let's get rid of that. We sure don't want, that's the other class. So let's see, I think we need to finish this. There's not too much. And then I've got another a real good Train PowerPoint. It's not too long on basically energy savings from using variable frequency drives on cooling tower fans, which can really be significant if you're set up with start-stop control, as a lot of the old towers were. So anyway, we'll go into that here in a little bit. So let's get on in. Whoops, let's jump in too fast here. Okay, so he's got some slides in here, and I can explain most of these. Some of these are a little cryptic, and I'm not real sure what he's getting at, but I'll do the best I can. But he's going to go through, make some comments on all 4 of these topics. Whoops, oh. Operator error here, going the wrong direction. Okay, so under this heading, selecting a tower, of course, and these are just kind of general comments that they're a little bit all over the place, but you're going to have to decide what capacity. I mean, how much heat am I trying to dissipate? And of course, if you're in the metric system, you could do kilocalories per hour, or in the US system, you'd probably be doing BTUs per hour, whatever. The units don't really matter. And then you would look at what's the flow rate. Have I got 1,000 GPM, or it could be in meters cubed per hour or gallons per minute, 2,000. If I've got that 1,000 horsepower or 1,000 ton chiller with a standard sizing on the condenser, that's going to be 3,000 GPM, and it's going to probably be a 10-degree delta T, is the way they're, at least in the old days, they were sized for. Now, you may be doing something different, to try to reduce energy a little bit more. But those are, key parameters that you'd have to look at. Well, okay, so when you're selecting a tower, you have to know the range. And of course, we're going to talk through these terms to try to pound home to you what they are. It takes a little while for all this to sink in, I realize. But we defined the range last time as the inlet water temperature minus the exit water temperature, or how much, how much of a decrease in temperature did we get in the water stream as a result of going across the cooling tower. So, standard numbers are 10, 12, but, for industrial applications, I've seen 20. It just depends on your process. So the range is determined, and the flow rate is really determined by the process. What is it I have to cool? Is it a chiller? Is it a bunch of industrial equipment? Whatever. So that's what's going to determine that. I mean, what's the spec on the equipment? You got a big furnace in there, and it says, well, I got to have 80-degree water. Well, the standard, for design condition on a lot of HVAC towers is 85. So if you were specing a tower for that, you probably have to upsize it for a given flow rate so that you could, in your hot weather, that you could achieve an 80-degree leaving water temperature to keep that furnace happy. Okay, approach, that's how close that cold water temperature leaving the tower gets to the wet bulb temperature. And remember, the wet bulb temperature is the primary parameter that describes the operation of the tower. Because what we're trying to do, a tower is trying to evaporate water into the airstream in order to cool the remaining water flow, and the temperature limit is the wet bulb temperature, okay? So we can't get colder than wet bulb. But the closer we get to wet bulb, basically the bigger the tower is. For a given flow, we have a larger and larger towers. So in order to get the approach to zero, you'd have to have an infinitely large tower. And of course, you can't afford that. So that's his comments. If you move closer to wet bulb temperature, that implies a bigger size cooling tower, which is more expensive. So, when you design these things, you have all these optimizations where you have to look at, okay, how much am I gonna spend on the cooling tower versus how's that gonna affect my operational cost year in, year out? Because that bigger tower will have a smaller fan on it. Okay, again, more stuff on heat load determined by the process. We've already said that. Required cooling is controlled by the desired operating temperature or temperatures. Again, the equipment's going to tell us what we have to have. So higher heat load, bigger size, more expensive. Makes sense. Wet bulb temperature considerations. Water is always going to be cooled to a temperature higher than the wet bulb. So, and the wet bulb is set by what? The ambient conditions. So every day, every hour, the weather is different. And so that wet bulb temperature will move around. And so, your ability to cool water, if you run the tower fans at their maximum, then your ability to cool water is going to move with that wet bulb temperature, plus whatever approach that you have under those conditions. And approach is not really constant. If it's really low wet bulb and cool outside, you may be able to get a little bit closer If it's hot and humid outside and you got that high wet bulb and you got high ambient temperatures, that's when you would probably get to your design approach, which might be a little bit larger than, for a lot of other hours of the year. Conditions at the tower site, and this gets referred to on several bullets through here, but I'll go ahead and give my interpretation of this. So you have to be careful if you have any moisture sources close to the cooling tower where you're going to site it. Maybe you're putting that thing real close to a lake. Maybe you've got some big pond with a spray fountain in it. Maybe you're putting it next to some other cooling towers. And those other cooling towers put moisture into the air. The lake can evaporate water into the air. And so if you just look at the average weather conditions for your town, those are not taken out there by the lake. They're taken at the weather station, which is most likely not close to those additional moisture sources. So you have to be careful, because what you really want to size your tower for is the conditions, the wet bulb, the moisture level of the air that's going to be going into your tower at the location it's going to sit. And so you may have this wonderful weather data file that was compiled at a station, 4 miles away, but you're sitting on the lake and your weather conditions are actually different, especially the amount of moisture in the air is considerably higher because of where you are. Or you may have a whole line of cooling towers where the moisture put up by some of these other cooling towers by recirculation is going to get pulled back in to yours. And so just using the ambient weather data can be a dangerous thing. So you have to really consider the actual location where this thing is going to sit, and then look around and see if there's any moisture sources close to it that would affect your sizing. Not to exceed 5% of design wet bulb temperature. I think that's the maximum wet bulb, but again, this is one of those kind of cryptic comments that is not 100% clear what he's getting to. Is wet bulb temperature specified as ambient or inlet? I'd say he's got ambient preferred. I would say inlet is preferred because that's the actual inlet condition. So I would kind of beg to differ with the author of these slides on that point. Can tower deal with increased wet bulb temperature? So if something happens and we get some additional moisture at a design at an aggressive condition in the ambient, are we still going to be okay with whatever devices we're trying to cool? Cold water to exchange heat. Okay, whatever that means. Let's see. Selecting a cooling tower relationship, range, flow, and heat load. Well, range is increases with increased heat load. Certainly. I mean, if you have a given flow and you're going to dump more heat, you're going to have a bigger delta T. Amount circulated water flow. So if we increase the heat load or something on a system, we may have to increase the water flow. Causes of range increase. Well, I mean, how can you change the range? The inlet water temperature can get hotter for the same exit water temperature, or the exit water temperature can get lower, or both. So if that happens to you on a system, you require that, or that additional load comes on, you may have to add cells, add capacity to make it work. I have no idea what he's talking about on this slide. I've looked at this several times, so I'm going to skip it. Okay. Fill media. This is important. There are different types of media and fill, and they have different performance characteristics. But basically, we distribute hot water over that fill media, and it breaks it up in order to greatly increase the contact area, surface area between the water and the air that's flowing across it to promote evaporation. So, you know, the type of fill and the efficiency of it is going to impact the electrical use for sure. It could affect the pumping cost, also the fan cost, which he doesn't, how much the fans have to run in order to be able to accomplish the required cooling. So fill media is fundamental in the performance of the tower. So now this is pretty good. I like this slide a lot. So he compares 3 different types of media. Film fill, he says, is more efficient. The splash, that's the kind of the old thing with the splash bars and all on the water. You had all these bars that were staggered in there, and the water would hit them and drop down and hit the next bar and hit the next bar and hit the next bar and just break it up into smaller and smaller little chunks of water as it would fall through. So you get more surface area, you get more evaporation. So you see some parameters. There's your L over G ratio. That's the mass flow rate of the water compared to the mass flow rate of the air. And so, you know, if that's greater than 1, we have a higher mass flow rate of water compared to air. The effective heat exchange area, square meters of area per meters cubed of fill, okay? The height of fill required, 5 to 10 meters, that's pretty tall. Pump head required, 9 to 12 meters, because, you know, that you got to pump the water up to the top of the tower. If the tower is taller, then you're going to have more pump head. And the quantity of air required is, you know, qualitatively high compared to the other 2 types. Okay, and so looking at the splash fill, the film fill, you look at the difference in area, effective area per meters cubed. It goes from 30 to 45 up to 150. So wow, you can see, you know, being able to make all that complex geometry of the film fill compared to just the simple splash bars is pretty remarkable. So we don't need nearly the height, and so we get reduced pumping head because we don't have to lift it so high in the air, and we require much less airflow, so we can have a smaller fan. So that's all pretty good. So these days, unless there's something strange going on, you're probably going to have film fill in your tower. And then this third column, I'm not really familiar with this, low clog film fill. So I guess that's a variant. I don't know, low clog, I'm not sure. That maybe refers to dirty water or dirty air or scaling up, I'm not sure. But anyway, you can see those characteristics. But the comparison between the splash and the film is really quite remarkable. And I think this slide does a good job in showing that. Okay, pumps, water distribution, well, he's not addressing pumps here, so it says, see the pump session. Optimize cooling water treatment. So this refers back to the cycles of concentration. So remember, cycles of concentration, if it's 1, that means that you're going once over the tower and you're throwing it all away. If cycles of concentration is 2, you throw half of it away every time it goes over the tower. If it's 3, you throw 1/3 of it away every time it goes over the tower. So the higher the cycles of concentration, the less water that we're going to bleed out of the system, but our dissolved minerals is going to go up. So, you know, it's a balance, and it depends on how crappy your makeup water is. I mean, you know, it's possible to treat your makeup water, you know, to take that stuff out, which means then you're not putting very much credit in with the makeup water. And so there's not as much in there to concentrate. And so you can use less water. Now, you know, how cost effective that is, it depends. You know, if you've got, you know, something like an industry has a large reverse osmosis system that has capacity they don't need, well, they might consider using some of that in a cooling tower to reduce the water cost, but water is usually pretty darn cheap, you know, so you got to look at the relative cost to decide. So we can save water and, you know, indirectly, perhaps some electric savings, not sure. Install drift eliminators. Now, cooling towers these days, you're almost surely to have drift eliminators, but if that tower is pretty old, they could be falling apart. And, you know, half of them could have fallen down into the fill. I mean, believe me, you start looking in cooling towers, you see all kinds of stuff, Coke cans, potato chip wrappers. I mean, Lord knows what you can find at the bottom of a cooling tower. And they do accumulate crud, and once a year, they probably have to drain the system and send guys in with shovels to shovel all that stuff out to keep the thing operating. Tower fans, obviously they've got to pull or push, whether they're induced draft or forced draft, the air through the tower. Anything that changes the air resistance, the resistance to airflow. If you have an increase, something gets bent or broken, the fill's not quite right, starts collapsing. You can't get the airflow through, so most likely you're just going to have diminished capacity until you fix it. And this last bullet on this slide is pretty interesting. I've never really considered this, but it may be, you know, if you're looking at an old cooling tower and, you know, eventually blades deteriorate, say on those propeller fans, there may be a more efficient blade profile. You know, the existing blades could be 20 years old, and it could be that you need to replace the blades, and if you look around, you might be able to find one with better efficiency, which means for the same airflow, you could use less power, and that could save you some money. So that's an interesting thought. And then the next presentation goes into the use of variable speed drives for speed control of towers, and that's really where significant savings are often available. Okay, so that gets us through our basic introduction to cooling tower. Oh yeah, and I want to tell you guys, Tuesday, Jill Rowan she is a Marley rep. She sells cooling towers in Nashville. I forget what firm she's with. She's going to kill me. She will tell you, but she's going to do the Zoom presentation next Tuesday. And I will send out emails. So I really want everybody to try to attend. And I'm not sure how long Jill will be on. I told her she could have the entire 80 minutes if she wants it. And she does cooling tower training. So she really is an expert on cooling towers, way beyond what my level of expertise is. And she's a really great lady. So I hope everybody can attend next class next Tuesday. It'll be our standard time. I think I've already sent her the Zoom link, so she'll just click in like the rest of us. I'll make her a presenter, and off we'll go. Okay, so let's see, let's just put this guy down. And let's go to this guy. And let me see, I can do this. I don't know if this presentation has many notes or not. Some of them do, but we get to see them in this mode if they have any notes. Okay, so variable flow over cooling towers for energy savings. And that's a little bit of a misnomer because the presentation is really about varying fan speed. So what we're going to look at is varying the fan airflow across the towers to reduce operating cost. There's the disclaimer. So if you do any of this stuff and your tower falls apart, SPX now owns Marley. So you say it's SPX at the top and Marley at the bottom. SPX bought Marley. Marley's one of probably the oldest cooling tower manufacturers out there. They have a lot of expertise. Okay, so purpose, so, this is for training. Intended to help us, increase energy savings in the existing tower using variable flow over cooling towers, even though they keep saying that, but there's maybe a little bit, but most of it is about varying airflow. Understand differences between crossflow, counterflow designs, how they impact. And if you did this in the right setting, you could get some continuing education or PDH credits, but you guys just get college credit, which is pretty good. So that's the outline. We'll go through that. Variable flow fundamentals. Okay, so yesterday, the good old days. Life was simple, controls were simple, energy was cheap, tower considered a constant flow device. Number of towers equal number of chillers operating. So in the old days, let's say you had 4 chillers. You would have 4 towers, and each tower would be chained to a particular chiller. So if you ran chiller number 3, you'd run tower number 3. And the rest, if that's the only one, the rest of the towers would be off, and the rest of the chillers would be off. But today, life isn't so simple. Controls are much more capable, and energy is not cheap. So some things have changed. So what are the opportunities here for operating towers differently? Well, how can variable flow save energy? What impact does the type of tower control have on the ability to operate it on variable flow? Are modifications or options available to enhance the ability to vary flow over a tower? What can go wrong when attempting to implement variable flow? And what are the risks? And so I guess the tail end of the presentation is more on the water side, but I really like the air side of this one, but we'll go through all of it. How much can I reduce flow in my installation? So they do get to that. Okay, so just some fundamentals. So less surface area requires more airflow, and more airflow is more horsepower. And so this is the example of selecting a bigger tower to get a smaller fan. So, for example, let's say we've got a 400-ton chiller, and so when you run their software, it'll come up with a whole bunch of different suggested cooling towers, that each one of which, at least the software thinks, would be acceptable. So you can see the top one, the 8403 TAN, has a 40 horsepower motor, and see the cost number is 1.0. So that's like the cheapest one that they think is acceptable. Because in this selection software, they're not going to give you a real price. What's the real price? Oh, good Lord. You can call them and see, these vendors, man, they hate to give you a price because, it depends. Well, is this part of a large job? Is this just you buying just the tower? Are you buying 4 other towers with it? So you get discounts and, there's no telling. So, and it'd be interesting, I may ask Jill to comment on the pricing and all the variabilities that can be involved in pricing of this stuff. Because, when it comes, they want to price it when it comes down to a bid situation, when they get all the construction documents in front of them and they say, okay, this is everything we're selling. Because, the architect and the design engineer, when they get the number back, they're going to say, hey man, that's out of budget. Come on. What are you charging me all this for? I estimated this at, $250,000 and you're at 325. Something's wrong here. You gotta work on these numbers. Okay. And so then you get pounded around. So, maybe you want to put in the large tower with a 15 horsepower motor, but say it's 0.49 times more expensive. And so maybe that's not going to fit the budget. So it depends. Are we concerned about operating cost or are we concerned about first cost? Well, the bottom line is we're concerned about both. But anyway, so you see our selections there. They ran 1200 GPM, 95 standard HVAC application in, 85 out, and 78 is the design wet bulb temperature. So say you can see the approach is what, 85 minus 78, so what is that? That's 7 degrees. So this tower is sized for a 7-degree approach and a 10-degree range. Okay, that's kind of the way all that stuff works. And you also get sound numbers, because sound is important, you know. Depends where you're going to put this thing. Is the sound going to be a big issue? And so, you know, as the tower gets bigger, the motor on the fan gets smaller, you're down to 59 decibels. That could be a deciding factor, you know. Sometimes you have to put up noise abatement enclosures around the tower, or you couldn't, you know, any type of equipment that's outside making noise can easily be objectionable, and you have to do something to knock the noise levels down. So that's important as well. Okay, so this is getting to be where the rubber meets the road, at least on airflow. So cooling tower capacity varies directly with fan speed. And so airflow also varies directly with fan speed. So the fan affinity laws, which we're showing one of them here on the bottom of this, but says basically in most fan applications, if I cut the speed in half, I cut the airflow in half. If I double the speed, I double the airflow. Now, if I double the speed, I better make sure that I have a big enough motor so I don't burn it up, but at any rate. So we see on that first bullet, 100% speed provides 100% performance or capacity. 75% speed provides 75% performance or capacity, and 50% speed is 50%. So they're linear up and down. So cooling capacity of the tower, roughly, now it's not 100%, but you know, within, you know, these types of arguments and training, it's pretty good, okay? So tower fan energy varies with the cube of the speed ratio. The cube. Well, at 100%, that ratio is 1. 1 cubed is 1, so if you're running 100%, you're going to pull your 100% full load power. That's pretty simple. But at 75%, you take 0.75 and put it in your calculator and cube it. That tells me my horsepower from 100% is going to fall to 42.2%. Or, well, that's what, a 58.8, is that 57 point, minus 2, so 57.8% reduction. So if you could deal with just 25% less airflow, you could save not quite 60% of the fan power. Whew. You know, I was looking at some TVA towers in the other class the other day, and they had 5 200 horsepower motors. That's 1,000 horsepower. How would you like to save, you know, 50-something% of 1,000 horsepower for a third of the year or something? That's worth having, you know. That's a significant chunk of change. At 50%, take 0.5 cubed, and you get 0.125, and that means that your power is going to fall to 12.5%. So that's 87.5% savings if you could deal with 50% of the airflow. Wow. Well, you know, I mean, when it's 95 degrees outside, no, you probably can't do that. But when it's 30 degrees outside and you know, your heat load is down, you might have a shot at that. And so that's 7/8 of the energy is saved on the cooling tower fans. That's on the fans. So that's pretty impressive. And then so they've got some examples here, and this is good for us. It's in terms of a big chill water plant. So the plant has 4 750-ton chillers and 4 in a 4-cell tower, or you can think of it as 4 individual cooling towers, but it's probably 1 tower with 4 cells. But each cell, you know, is like a little independent cooling tower. And so that's 7,000 or 9,000 GPM. Let me see, that's 15. Yeah, so the total tonnage is 750 times 2 is 15, times 2 again is 3,000, and at 3 GPM per ton, 3,000 tons is 9,000 GPM. So if we're running full out, all 4 chillers, we're going to be circulating 9,000 GPM of condenser water. And you need to get used to looking at these numbers: 95, 85, 78, 95 water in, 85 water out, 10-degree range. 78 is the wet bulb at that design condition, so we got a 7-degree approach. So there's your selection. That's a tower model number, and we've got each cell has a 40 horsepower fan. Okay. Now, so let's say this is a typical August day. It's hot, but it's not, it's 85 degrees. It's not our design day. And so our cooling load is 75%. Okay. So we only have to run 3 chillers. Okay. So the old way of doing it is to run 3 chillers and 3 towers. So if you look at the fan horsepower, you've got 3 chillers, full load. So you got 40, 40, and 40, because each cell has a 40 horsepower. Okay, so we're 120 horsepower. And the flow rate is 6750 GPM. That's what, 75% of our 9,000. And we got 1 chiller off. And so, and that fan, that tower is off and the fan's off. Okay, so we're not putting any GPM across it. We got automatic valves and all that sort of thing. Okay, so that's the old way of doing it. Okay. Let's see. So let's go on to the next slide. Well, what could we do differently? Well, let's run all 4 cells. Okay. And so I only need 75% of the cooling out of each cell, because my load is only 75% of my total plant capacity, which means that I can run each tower fan at 75% speed, because speed is capacity is airflow. Well, so what happens? So that, what was it? The fan power falls to, what was it, 42.2%, something like that at 75. Isn't that what we had up there? Yeah, 42.2%. So 42.2% of 40 horsepower is 16.9. So I'm running 4 times 16.9. So guess what? I add all that up and I'm at 67.6 horsepower. Here, I'm at 120 horsepower. Dead gum. And you know what? If you've got a chill water plant set up like that, the vast, vast majority of the whole cooling season, you don't need all 4 chillers. It's really, really hot, okay, but maybe a lot of July and August you do, but you get into September, October, November, December, heavens no, your load falls because it's not hot outside. So this is pretty compelling. Okay, well, okay, so let's carry it one step further. So now we're at 50% load, and we're only going to run 2 chillers, but we're going to run all 4 towers. So we got 4,500 GPM, and so I guess we're going to divide that evenly amongst the 4 towers. And so at 50% load, the tower energy is 12.5% of the 40 horsepower. So that's 5 horsepower per cell. That's 20 horsepower. The way I would have done it with 2 chillers fully loaded, I would have run 80 horsepower. And so that's a 75% energy savings versus the traditional way of operating. So you kind of get the picture here. This is starting to look like a pretty good idea, and this is the way that cooling towers need to be controlled. Okay, now this starts getting into the water flow side of it. Well, personally, I find the water flow side of it to be dull and boring, and I really like the fan energy savings. So, sometimes I just stop here, but for this class, we'll go on through it because I mean, you need to see all this stuff. So there are limits though on how low you can go. You can't just keep reducing flow over a tower. You can't run at 10% flow. Okay, you're going to run into all kinds of trouble. But so for a specific tower, you really need to go back to the manufacturer and see what their minimum recommended flow rate is for that particular tower. And then you might even want to not reduce it quite to that level, just to be on the safe side. So that's what they're saying here. Work with your cooling tower guy to determine reasonable minimum flow rates. Well, for example, here, let's say that you're running just one chiller, and say so they can't run all 4 cells because that would violate the minimum flow. So it's 2250 divided by 4, whatever that is too low. So they're saying, okay, in order to respect the minimum flow, I'm still going to have to run 3 towers. Okay, and so so that puts me at 33%, and so that's still pretty good. But that's 4.5 horsepower out of would have been 40 with one chiller before. So there you go. So that's an 88% savings. Okay, but of course, Murphy is always lurking. And so what can go wrong? Well, plenty can go wrong if you reduce flow too much. Water distribution, unpredictable performance, ice formation in cold climates. Are there any cooling tower designs, crossflow, counterflow, that would help you mitigate or eliminate these problems? So we'll get into that a little bit here. So now notice the propellers, the fans in the top. So these are both induced flow towers because we're sucking the air through the tower and spitting it out the top, which is good for recirculation control. And so we've got the crossflow and we got the counterflow. So the counterflow, the air kind of comes in that chamber beneath the tower and then rises vertically through it, counterflow to the water, and the crossflow, it just kind of comes across while the water's falling down. Okay, so we'll do crossflow first, water distribution. So we have gravity flow basins. And so you can kind of see a little bit over here. This is just a cover. They've got the cover off of this one. So the water, when it comes to the top of the tower, fills up in this basin to a depth of 2, 3, 4 inches, whatever it's supposed to be, roughly. And then that pressure forces it down through these nozzles, but it's all done by gravity. That's gravity flow. Get lots of nozzles, about 260 in a 400-ton tower. Nozzles are close together, so it's easy to distribute water over the fill. And of course, you've got little chambers like that all around on both sides. And the pump pumps it up, and you've got a pipe going in here, and that basically feeds water out into these basins. And there's another pipe coming on the other side to feed the basins over there. The head, or the height of water in the basin, is a function of nozzle size and flow rate. If you put too much flow, it can't fall through the nozzles, and you can overflow the tower. And I've seen a few towers. You go out there and look at it, and the water is just streaming down, overflowing, coming out. And you go, I don't think that's right. Usually that's because nozzles get plugged. They get a couple of potato chip wrappers, make it somehow into the pump and get up there, and then it plugs 3 or 4. You start plugging 3, 4 nozzles in each basin, and pretty soon you're putting more water in than can drain out. So if you put too little, you don't have enough pressure. You don't fill the basin to the right level, and that little bit of head is enough to force the water through the nozzles correctly. So they talk about minimum max water depth over the nozzle, someplace between 2.5 inches minimum to 5.4 inches maximum. Okay, Counterflow Design has a kind of a fundamentally different distribution. So what we have here is the pump pumps into like a header, and then it's a pressurized spray system. And so we have fewer nozzles, and it's the pump head, the pump pressure, that kind of forces the water out into the proper distribution pattern so that it falls down across the fill. So we have a lot fewer nozzles, and they spray over a larger area. They're saying about 60, and what do we have, about 260. So we got in the Crossflow Design, so we've got only about 60 in this 400-ton tower. They're further apart, and nozzles have to throw water laterally to cover the fill. And of course, that's one of your goals, is to, you got to distribute the water well for the tower to work. And so this is showing with the fan on high speed. So it's blowing the fan. It doesn't show the fan, but it's blowing air into the bottom part of the tower, and then it turns and goes up through the fill like this. These things are just too small to really see. These are for different nozzle sizes, different pressure drops. This is for cross-flow and counterflow. There's K values for the nozzles and all that, but it's, we're going to just pass by this because you can't really see it very well. Even if you blow it up, it's hard to read. Okay, so variable flow in cross-flow designs. Okay, so Marley has this thing they call Nozzle Cups, which are kind of interesting. So they're totally passive. There's no moving parts. It divides the hot water basin into like an interior and an exterior sections, or they call them outboard and inboard sections. So it manages variable flow automatically, maintains adequate basin head, maintains uniform airside pressure drop to minimize drift, minimize ice formation in freezing weather, ensure uniform air-water contact, and provide consistent off-design performance. So these nozzle cups turn out to be a pretty good idea, and I don't know who came up with this, but it probably was not a PhD someplace. And this is what they look like. So on the inboard nozzles, they place these cups. And so it just basically, the water can't get into these inboard nozzles until the water level is fairly high in the basin, okay? And so if you have a relatively low water flow, then you're not going to have the depth to overflow and get into the inboard nozzles. And so the water is going to go, and it'll go through the nozzles on the outboard section, wetting this side of the fill, okay? So water overflows for the full flow. Now for the full flow, when you're doing your rated capacity, these things are sized so that we've got enough depth of water in here that all of the entire fill gets wet, okay? So water overflows, nozzle cups. Again, this is full flow example. Entire fill volume is active, nozzle cups have no effect. So it's going to operate just like it would have otherwise. Intermediate flow, so we have reduced head or reduced elevation in the hot water basin. Some water flows over the cups, full distribution on the outboard section because we've got all this elevation over these that don't have nozzle cups on them. So we have lower water loading or flow inboard. Uniform airside pressure drop prevents air channeling. So you got to be careful that, see, all this air is sweeping in the side of this thing. If there is a place that doesn't have the same amount of water, doesn't have the same resistance to flow, then the air will rush through that section and you won't get adequate cooling through the rest of your water flow. So you got to be concerned about that's what they call channeling. Benefits of the nozzle cups: improved cooling efficiency, reduced operating cost, lower risk of ice formation. Okay, so this is the intermediate flow. And this is, now this flow is in terms of water falling down. Okay, then the low flow example, say that case where we had cut back the 33% flow for the 3 cooling towers with the 1 chiller, then we don't have so much flow. And so the water level is not sufficient to get above the nozzle cups. And so this side is actually dry of the fill, and all the water falls through the outboard section. So low flow, reduced head and basin, no water flows over the cup, all water is outboard, rear of fill remains wet, this side, I guess. Benefits: eliminates risk of scaling, uniform air side pressure drop, and prevents air channeling. So this is what Marley does. Now, each manufacturer is going to have their own approach to extending the different flows, being able to go down to a low flow condition on their towers. Crossflow inboard inlets cause problem. Oh, this is if you put them on the other side. No, this is wrong. Do not do this. Important. Water inlet needs to be on outboard side of the basin and nozzle cups on the inboard side. If inlets are inboard, cold air enters the dry fill, increasing potential for ice formation. Okay, because there's going to be droplets. I mean, this stuff probably not going to be completely dry, and so because remember, this water is a heat source, right? The whole purpose it's coming out here is to get cooled down. So this stuff is fairly warm. So, your ability to avoid icing means that you want this cold air to hit the full flow, which means you want this flow to be on the outside. Having the potential just a slight bit of moisture out here, that stuff's going to freeze like crazy because it doesn't have enough heat capacity to not freeze. Okay. So transition zone, dry to wet fill. So you don't want to do it this way. And I'm sure that was probably discovered by trial and error. I don't know, back in the day. Okay, other things we can do, we can have what they call these integral inlet louvers. Important, make sure film fill has integral inlet louvers to minimize ice formation. So these are designed to reduce the potential for ice formation. Icing can damage fill, reduce performance. No splash surface eliminates winter splash out and reduces icing. Keep heat water close to the louvers. So they're specially designed in order to do that. So that's something that you would want to make sure, if you have a tower like around here where it's going to get down to, I don't know, in the low 20s. As the polar vortex rolls through. Okay, Crossflow Design. So we're showing here, nice picture. No integral louvers, we're all iced up. Integral louvers, we're not iced up. So look, I'm sure this is a little bit of marketing, but nonetheless. Oh, and there's a thermometer there. What is that? 0, looks like it's like below 0, I don't know, can I blow it up? Yeah, it's pretty nippy. That's like up in Wisconsin or someplace where they're going to get the full polar vortex instead of us. Okay, so now we're going to look at counterflow designs. That was all Crossflow. No modifications are available for counterflow designs to enhance variable flow performance. So this would tell you that unless you have some particular reason that's driving you to this counterflow design, if you have a possibility of changing flow rates through the tower, you don't want a counterflow tower, you want a crossflow tower, okay? Limited ability to run at low flow rates, because what's going to happen in those nozzles, if you're going to run less flow, you're going to have, the pump's going to have to slow down, and you're going to have less pressure. And when you put less pressure into this spray header up here that's going to spray the water out into the fill, you're not going to get full coverage on the fill. So less pressure at spray nozzle, reduced atomization of droplets, less energy to throw water laterally. So, when you're at full load, you get nice, distribution like this. So, this is okay, but when we go to the next slide, then this is where you get into, can get into trouble. So if you reduce flow too much, generally more than 30%, so you can only go down to 70%, which, is some reduction, but not great. Generally you get uneven water loading, because say you don't have enough pressure, and so this flow pattern out of these nozzles doesn't completely wet the fill. And so you have these channels in the fill that don't have any water in them, and so they don't have any pressure drop. So your air is going to preferentially channel up through these dry areas, and it's not going to penetrate the water, so you're not going to have good contact and evaporation. So there you have it. Lower air side pressure drop in the sections with less water. Air takes path of least resistance. More air in drier sections. Less air in wetter sections, resulting in bad thermal performance, risk of ice formation, and greater risk of scaling. The other thing is, where you have this air flowing through and this stuff is just barely wet, then you can evaporate all of the water, and it's going to leave the minerals behind, which is going to takes the form of scale, and then you start scaling up your fill, and that's a bad thing. So this counterflow designs are not really looked at much for flow variation. There's some more of this nozzle physics. You can look at that. I'm not going to get into that. Things to remember: all nozzles operate under the same physics. Head varies with the square of the flow rate. Different manufacturers have slightly higher or lower head limitations. Turn down depends on where you start the curve. Counterflow towers may require a trade-off between nozzle size and ability to turn down. Crossflow towers do not. So basically, I think what this is saying on this counterflow tower is you probably don't want to get into this. Okay, we're doing pretty good here. Cold weather operational tips. Okay, so when it gets really, really cold outside, what are some operational procedures that we should implement? First one, circulate water, only circulate water with a heat load, because you want that warm water out there interacting with that cold air with a hope that you're not going to freeze up. Maintain adequate flow over the tower, or use a bypass. A bypass is piping where if it's cold enough outside, you may not have to run the fan at all, or you may be able to put just a portion of the flow and just let it fall through the tower, and then mix it with the portion that bypasses in order to get an adequate cooling. If you're 0 or -10 or something like that, it's cold enough outside, you may not have to run the fans at all. Use a two-way, not modulating bypass to cold water basin, not into the condenser water supply piping if necessary. I'm not real sure what that means. They don't show piping diagrams, so I'm going to pass over that. Use VFDs on all fans. If you're ever involved in speccing a tower these days, you probably want VFDs on all your fans. Ramp speeds up and down together. You know, if you're running however many cells you're running, run them all at the same percent speed. Use thermostatic control for fans. Use a reasonable cold water set point. Minimum cold water would be the range plus 32. If you had a 10-degree range, then you might be at a 42. Minimum set point would be a 42. Do not run the fans continuously in reverse, and monitor air inlets for ice formation. So in really cold weather, keeping these cooling towers from icing up is important. Okay, well, what if you do? What if you screw up? You forgot to check for yesterday and you came in and they're all iced up. So first step, cycle the fans off. This is usually all you need to do to de-ice the units, because you got this warm water up at the top. If you don't pull any air in, just let it circulate that warm water and fall down over the tower, and then, you know, some period of time that water is warm enough to just melt the ice. If that doesn't work, use de-ice procedure. Cycle fan off and wait for it to stop. Run fan in reverse, 5 to 10 minutes at low speed, approximately 30%. So that's the reason you wanted it to stop, is you didn't want it running one direction and then throw it into reverse. Kind of like do that with your stick transmission on your car or something. Not a good plan. Cycle fan off and wait for fan to stop. Assume forward operation. Monitor and repeat as necessary. Hourly ? Don't wait for heavy ice accumulation. Catch it early before it gets really, really bad. So the VFDs can run the motors in reverse. So that's another very handy characteristic of the VFD. So you just run it backwards. And so then you're pulling air in the top of the tower, and see that ice is going to be on the outside of it. And so then that air gets forced through the water, which warms it up, and then it attacks the ice from the backside and melts it. So that's kind of the idea there. Let's see, cold weather operation tips, options to consider. Basin heater package. If you're going to be outside, I mean, it's possible to, if that basin sets outside, you could just, I mean, even with ice, even with flow through it in the corners where the water is pretty much stagnant, if it's cold enough, it can freeze. So you can just get electric, they're usually electric resistance heating elements, and you know, you pick a set point 40 or 38 or something, and just maintain that water at that. Don't let it get too cold. Can be electric. Usually I think they're electric, but it could be steam or hot water. You got thermostatic controls. Another idea is, if you're doing the design, consider having the sump inside. So the cooling tower itself sets outside, but then the water falls down and actually through a pipe, and the sump is down inside in conditioned space, so that you don't have to worry about it freezing up. Gravity drain on shutdown, fail-safe, trades energy for real estate, must be properly sized. So that's another idea. Okay, wrap up. Let's see, variable flow offers big energy dollar savings potential. Remember, tower fan energy varies with the cube of the speed ratio. Inherent design differences between cooling towers. Crossflow can be easily modified for variable flow. Counterflow cannot be practically modified. And opportunity for variable flow and counterflow towers is significantly smaller than for Crossflow. There are common misconceptions about how much flow you can reduce with certain types of towers. If you want to reduce flow, talk to your rep. Engineers at the company should know. For new or retrofit variable flow applications, pick Crossflow tower for maximum flexibility. Let's see, back to the common question. Well, I think we should have, that's what we should have learned as we go through this. Other lunch and learn items, whatever. Remember, update, apply for PDHs. Okay, well, that's good. That worked out pretty well. We're just about at the end of class time today. I have a little bit more. Well, let's see, Jill will be here on Tuesday. And then depending on how long she goes, if I have about 20 minutes, I can probably finish up. So we're coming to the end of cooling towers pretty quick. And so when we get finished cooling towers and all, we'll be looking at a quiz. So not next week, but the week after. That's kind of where my other class is too. Be thinking about, we'll schedule it later so we can talk about what date works best for you guys. I mean, I'm flexible. But at the end of cooling towers, we're going to be looking at our first test, okay? And it'll cover everything up through cooling towers that we've talked about. It will be an iLearn. It will be a whole bunch of questions. If I can come up with some little problems for you to work, even though we haven't really done number crunching problems. So most of it will probably be true, false, multiple choice, maybe fill in the blank, that sort of thing. So we'll talk more about it as we get closer. That's all I got. Anybody got questions or comments? Okay, guys, hope everybody has a great day. Stay safe, and please be on Tuesday when we get Joe Rowan to talk to us. Take care.